Know your gas limit. Stay within it. Don't make mistakes or get invalid drumped. Yo, not just to pre-compile a change of opcodes. We're here to sustain and scale all the full nodes.
Proof of stake is hard, but what I do know is when we learn a shard, we'll change the whole game, though.
E2.0, yo. E2.0, yo. E2.0, yo. E2.0, yo. Shard 3, BLS, and Lamport, and all of this crypto just sets the stage for Merkle proofs, plasma chains, plap, plap, ZK snarks coming over, quack, quack, privacy scaling in a snap, snap, constant products, oracles, tap, tap, Merkle proofs, plasma chains, plap, plap, ZK snarks coming over, quack, quack, privacy scaling in a snap, snap, constant products, oracles, it's all about the dApps.
Every user, every wallet, every dApp. ZK miners, double signers, every villain with attacks. Every channel operator, every flap. Every phone node, every staker, everyone will interact. And that is that.
Constantinople is done. Fork, plasma group L2 engage. No fork, all of it coming in waves. Fork, your boy Carlos is from New York.
Plasma, state channels, layer 1, layer 2, layer 4, 8, 16, binary, Bitcoin, blockchain, trust, human coordination. You know the drill. Merkle proofs, plasma chains,
plap, plap, ZK snarks coming over, quap, quap, privacy scaling in a snap, snap, constant products, oracles, tap, tap, Merkle proofs, plasma chains, plap, plap, ZK snarks coming over, quap, quap, privacy scaling in a snap, snap, constant products, oracles, it's all about the dApps.
Not just a recompile or change of opcodes. We're here to change the rails, upgrade all our full nodes.
EWASM is hard, but what I do know is with abstract accounts we'll change the whole game though.
E2.0, yo.
E2.0, yo. E2.0, yo. E2.0, yo.
Logo octahedral, we must coordinate. But we ain't no cathedral, no one subordinate. Every team and every project we can get far. Subvergic biologic, we work like a bazaar, yeah.
Staking all in the first phase. Spork, all of this coming in waves. Spork, deposits coming in waves. Spork, your boy Carlos is from New York. Yeah. Everybody, E2.0, yo. E2.0, yo. E2.0, yo. E2.0, yo.
E2.0, go have some bro, yo.
Hey.
Difficulty,
Hey.
ice age, meltdown. Layer 1, layer 3, 9, 27, ternary. Build your own hash functions for maximum security.
This is what happens when you code a lot.
Liveness failure. Less than
Liveness
2/3 online.
Oh, yeah.
Slashed.
The outro is really long. What am I gonna do?
I'd now like to welcome to the stage founder of LinkTime, Pandia Jiang.
Hello. Hello, everyone. Happy to meet you again, and happy to meet so many new friends coming to EDCON this year. The Ethereum community is a great community, and it is exciting to see it grow so much with every year. Oh my, yeah, sorry. First, most importantly, I want to thank everyone who helped us to make the conference happen. Although the market is a little cold, but our sponsors are warm. I want to thank them. They have given us so much support to help us to make this event happen. We try hard to make the event as sensible for people as we can. We offer many developers and student discounts, so we rely on support of our sponsors. Thank you very much. This year, we have even more community supporters and media than before from all over the world. Now, I want to thank all the speakers. Most of them fly very far to come to Sydney. This time, we have almost all the core researchers and many developers of Ethereum too. The exciting project to make Ethereum hundreds of times more efficient and scalable with proof of stake and sharding. We also have many researchers and developers of Plasma and many Ethereum applications, both for profit and non-profit. The hard work put in by all of these people, both old and new, is what continues to make the Ethereum community great. Let me introduce EDCON for new friends. This is our first EDCON in Paris in 2017. And this was our EDCON in Toronto last year. And now this is the EDCON Sydney. I hope you will like. Our EDCON are held annually, usually in April or May. For the next EDCON, we are thinking where we should go. If you have a good suggestion, please email to us. We are looking for locations that are easy to travel and get around. And that can hold more than 1,000 people and easy to get visas. Aside from EDCON events, we have also organized a large Ethereum meetup like this one in Shenzhen, and this one in Bangkok in February last year, and this one in Beijing last year, and this one in Hong Kong. Hope to see you in more cities. To help you enjoy EDCON, I need to introduce some details about the conference this year. Our presentations will be happening in the main conference and the main conference room and the sub-conference room. And there will be parties and happy hours events organized by community organizations. You can look at the EDCON website to see what the events are. Okay, here is a map of the conference venue. The map is also available at the front desk. If you need, you can go there to check. We hope that EDCON can be an opportunity for people from many countries and communities and many backgrounds, including technology, business, and research to come together. This year, we have people coming from at least 15 countries. We try to be flexible and meet the needs of different speakers and give as many people as possible a chance to speak. We believe in treating people fairly and try to choose speeches to bring as much value as possible for all attendees. We want this conference to not just be about presentations, but also give people an opportunity to meet and talk to each other, and hopefully find opportunities to cooperate in the future. Let me introduce us now, LinkTime. In fact, we are a technology company, but we like and are good at making community events. EDCON is our biggest and best conference series. We are also developing an Ethereum wallet called Panda X. Panda X is for Ethereum wallet, including the ability to create and import accounts and make payments, support for Ether and ERC20 tokens, a dApp browser, and token swap, and many more features. Hope you try and look forward to cooperating with you. Yeah, this EDCON maker is offering an airdrop of 10,000 DAI that you can claim. To claim your share, you scan the QR code to install Panda X. Find the EDCON dApp on the application page. Click the registered address icon and show the QR code to the staff at the registration desk. Then you can use DAI or XDAI to buy any EDCON souvenirs. We also have UniTime, a global Ethereum community platform. Anyone is welcome to publish their contents on the site, and we hope to see more people start using it. We can also help you build a technology community in China or Asia. We can help you with PR service in China, and we can organize online or offline international blockchain events. I hope that you can enjoy the conference in the next 3 days, and I hope to see you again next time. Finally, if you want to contact me, you can find me here. Thank you. Okay, let's start the conference. Thank you.
What's up, everyone? Welcome. Thank you for all waking up so bright and early. So I'm Ben. I'm going to be introducing some of the lovely speakers this morning. Before we do that, I know that Pandia has put an incredible amount of work and time and energy into this project, so I think we should give her another round of applause, seriously. Thank you. In any case, our first speaker probably needs no introduction in this room. But he's going to be talking about the future of ETH 2.0 and some research. So let's please welcome to the stage Vitalik Buterin.
Okay, hello everyone. Hope you've had a good morning. Raise your hands if you have a good morning. Raise your hands if you haven't. This side of the question always gets no answers for some reason. It's strange. So today I'm going to talk about one of the technical developments that's not going to become relevant to Ethereum 2.0 immediately. It's a slightly later stage thing, so possibly phase 2 shortly after phase 2. I've been calling it part of phase 3, which is the introduction of a CBC Casper into the Ethereum 2.0 proof-of-stake blockchain. So first thing, I should start off by introducing what CBC Casper is, right? So CBC consensus is this a new school of safe under asynchrony Byzantine fault-tolerant consensus, meaning the kind that works, originally invented by Vlad Zamfir. And the main theme of CBC Casper is that you have basically a proof-of-stake chain, so you have validators, and validators keep on making blocks, and when they make blocks, they make a block on top of the chain that they consider to be the best chain. And they might pick this with what Vlad calls an estimator, I call a fork choice rule, and fork choice rules are pretty common. So for example, the longest chain rule in Bitcoin or in Ethereum is a fork choice rule, except here there's a twist, which is that unlike the longest chain rule, where given any particular chain, there's always the possibility some longer chain exists. Here there exists this possibility of a kind of lock-in mechanism, where once enough validators build on a particular chain for enough rounds, then according to the rules of this fork choice rule, it's like that chain becomes locked in. It's like not possible to switch to voting or building on another chain without a huge portion of validators like basically committing provable violations, which means they get their deposits slashed. So In CBC Casper, finality, the concept of when you know that a block is not going to be reverted is client-side. So what this means is that you don't need to choose hard thresholds in protocol. Like the number 2/3 that you might see in BFT protocols more commonly does not appear in CBC, right? Like you can choose for yourself a threshold of 2/3, but you can choose for yourself a threshold of 0.8 or 0.55. And every user personally has the ability to kind of choose for themselves their own trade-off between aliveness and safety. So LMD Ghost, it's this fairly important building block of at least the version of CBC Casper that I'm going to be presenting here, right? So what is LMD Ghost? So it stands for Latest Message-Driven Greedy Heaviest Observed Subtree. So it's an adaptation of the Ghost protocol created by Yonatan Sobolensky and Aviv Zohar back in 2013 to a proof-of-stake context. And the way the Ghost protocol for proof of work worked is basically that instead of looking at the longest chain, you do this kind of block-by-block procedure where every time you reach a block that has 2 children, you pick the child that has more blocks in total supporting it, even if those blocks are not part of the same chain. Now, in latest message-driven Ghost, which is this adaptation to proof of stake, we don't look at all of the blocks that have been made because, like, unlike in proof of work, where making 10 times more blocks requires 10 times more computing effort, in proof of stake, you can sign as much as you want, so there's not much more points in counting. And so we look only at the most recent messages of any node as evidence of the most recent opinion of what that particular validator is favoring, right? So now, if we can look at this through a diagram, so let's assume a kind of simple model where the only thing that happens is blocks. You don't have attestations. You don't have any more complicated messages. You just have blocks. So you might imagine time being kind of split up into epochs. During each epoch, every validator has a chance to create a block. So here we're assuming 5 validators, where each validator makes a block once over here on the left, so A, B, C, D, and E are the validators, and then each validator makes a block on the right. And so if, from your point of view as a client, your view, so the blocks that you have seen, end with this, then you figure out what the latest blocks are created by each validator. In this case, from A, it's going to be this one. From B, it's going to be this one. From C, it'll be this one. From E, it'll be this one. And from D, it's still this one because we haven't heard a block from D in this epoch, right? So this is what latest message-driven means, right? So now, what does Ghost mean? So the idea is that we're going to focus on these 5 latest messages, and we're going to assign a score to each block, where the score of the block basically is the total number of latest messages that are supporting that block. So this block only has 1 block supporting it, which is that block itself. This block only has a score of 1. This block has a score of 1. This block is supported by itself and by this block, so it has a score of 2. This block has a score of 4 because it's supported by this, 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 and this. Now it's not 5 because this block itself is not a latest block, and so it doesn't count. This is also 4. Now here we have 1, and then this finally goes up to 5. Now, you might notice that scores go higher the older a block is, so we're not going to just pick the block with the highest score, right? The idea here is that we're going to start with the genesis block, so start over here, and then if there's 1 child, we hop over to the child, and then if you have a choice between 2 or more blocks, then you pick the side that has a higher score. So over here you pick bottom, then you go to the right, and then over here you pick middle, because middle has a score of 2, and then you go forward, and this ends up being your head. Now, you might ask, well, why do we care about using LMD Ghost, right? So for example, just a simple longest chain rule would also pick this block in this particular case as the winner, because this block is the unique block that has a chain of length 6, and so even on the longest chain rule, it wins as well. So why not just use the longest chain rule if it is simpler? So The reason why we use LMD Ghost is that there's two parts to it. One of them is a kind of common property of Ghost in general, which basically is that longest chain rules cannot take into account information from frequent parallel attestations. So what does this mean, right? So what this means is that in the current Ethereum chain, you have a block coming once every 14 seconds. And so on average, something like over 91% of all blocks make it as part of the main chain. And so we can kind of not care about what those blocks that are not part of the main chain say because they don't really affect things that much. But now imagine we wanted to have a chain that comes to consensus faster. And so instead of one block every 14 seconds, we had 14 blocks every 1 second. Now, if you do something like that, then almost all of those blocks are not going to end up being part of the same chain, right? Just because of network latency. If I publish a block, by the time that block reaches the entire network, there will be 100 other blocks that other people will have published. And so the kind of depth of the chain, the length of the longest part of it, will be maybe 1% of the total number of blocks. So the problem with this is that if you have an attacker, then an attacker just running on their own server could more easily just create a chain which is much longer because they can perfectly coordinate with themselves. They don't have any network latency. So, but in reality though, even if you have an attacker that can make longer chains, like there's plenty of information that says that the chain the rest of the network is working on has more support, right? You can just look at it and you can see that there's like 100 times more people building on the real chain than there are people building on the attack chain. And so the question is, well, how do we have a kind of formally defined fork choice rule that actually takes this information into account? And LMD Ghost is the answer, right? If two blocks appear in parallel, they still both count as support for whatever their common ancestor is. Another interesting property of LMD Ghost, and this is very important to CBC finality specifically, and specifically important to Ghost in a proof of stake context, is that the minority can never beat the majority regardless of how many messages the minority sends. So in this particular case here, right, we have 5 validators, once again, and you might notice that 4 of them are kind of peacefully, happily coordinating on building up one chain. I mean, you see C and D make a little bit of a mistake, but otherwise it's just going on fine. And then you have B off in a corner, possibly disconnected from the network, possibly trying to attack it. Now, imagine B makes 500 blocks. If you use the longest chain rule, B would win. If you use proof of work style Ghost, B would also win. If you use LMD Ghost, B would lose because all of those blocks come from B, and we only count the latest message anyway, so when you make a new message, it overwrites everything that you said before. So from these two properties, what we get is a fork choice rule, which is both kind of very friendly to ETH 2.0's goal of trying to coordinate on blocks very quickly, and at the same time, something that looks like it might actually kind of finalize in the same sense something like Casper FFG finalizes. So let's take a look at this view that I showed you in this slide more closely, right? So let's assume the thing at the top is your global view. So you are happily running an Ethereum node, and your happy Ethereum node has received these blocks from the network. So that's your global view. From your global view, you can infer things about the local views of each of the validators. So for example, one thing you might notice here is that A made their most recent block over here. And so if A made the most recent block over here, that means that at that recent point in time, A was aware of these 4 blocks, and at that particular point in time, A considered these 4 blocks to be the latest messages. If you look at C's view, C built a block over here, which means C was aware of these 4, which means you know that C sees that these 4 latest messages are kind of pushing the fork choice rule in this direction. You know the same thing about D's view, and you know the same thing about E's view. right? So each of the 4 validators, except for B, sees the chain and sees that everyone else is also building on the same chain. So from this information, we can make a claim, right? And the claim basically is that unless at least 2 validators make blocks that violate the protocol rules, so make blocks that where you can just take that block, put it together with a block the validator made before, and you get a proof that the validator violated the protocol, then the chain will, basically, unless at least two validators break the rules, no validator except B has the ability to make a block on top of the top chain. And so the only thing that can keep growing is the bottom chain. And so we say the bottom chain, or specifically A, is finalized with a, quote, safety margin of 2, right? So how do we justify this? Well, first of all, it's a rule of CBC Casper that for a block to be valid, that block must be the block's parent must be the result of executing the fork choice rule given all of the messages that that chain knows about. And so here, well, can A build a block over here, right? So first of all, for A to do this, then A would build a block over here, but then no one else had built a block yet. And so, well, A would be clearly violating the rules because A moved from a chain that has more support to a chain that has less support. Can C legally move to the top chain? Well, no, because C built a block on this chain that's supported by 4 validators, and this chain has 1 validator, so C can't legally move over. Can D legally move over? No. Can E legally move over? No. And it turns out that you need any 2 of these validators to break the rules and illegally move over to the top chain for everyone else to be able to follow and for the top chain to win. So this is why A is finalized with a safety margin of 2. Now, you might notice here that this concept of safety is completely subjective, right? All that we have here is validators following a fork choice rule. We just have validators following a version of Ghost that's been adapted to proof of stake, and that's been adapted to this context of a kind of bounded validator set. And out of this, you have this concept of finality. Even though you do not have an explicit 2/3 threshold, you do not have an explicit concept of preparing and committing, you don't have any of these kind of explicit ideas that exist in either Casper FFG or more traditional Byzantine fault-tolerant consensus algorithms more generally. Right, so this seems like what we've basically managed to do is we've managed to build this concept of finality, which previously was a more kind of the domain of these BFT algorithms, on top of a proof of stake algorithm that looks very chain-based. So it looks very similar to just some of the older proof of stake algorithms that people have been doing for the last 5 years, except by switching from longest chain to LMD Ghost, you just kind of unlock the ability to get this finality property, right? So basically what this says is that A is finalized unless 2 validators, unless 40% of the validator set is willing to burn all of their money to cause the consensus to shift over. So more generally, in the context of LMD Ghost, there exists a heuristic called the 2-round Queeg oracle, which says if there exists a 1/2 plus P sized subset of validators that all support the same chain with 2 consecutive messages, so 2 rounds of messaging from 1/2 plus P, then the earliest of the blocks signed in those 2 rounds is finalized with safety margin P. Now, if you want to solve for kind of maximizing safety and maximizing liveness, then you might want to set P to be 1/4. And so if 3/4 of the validators support the same chain with 2 rounds, then you get a safety margin of 1/4. So the 2-round Queeg oracle is sufficient, but it's not necessary for finality. So there's also the 3-round Queeg oracle, there's the n-round Queeg oracle, there's potentially other kinds of oracles. So there's this extremely large space of heuristics that you could potentially use to kind of compute whether or not finality is happening locally. So cool things about CBC Casper, right? So why is this potentially interesting? So first of all, different clients can privately choose different required safety margins at which they show a block as finalized. And especially if a client believes that some subset of nodes are permanently offline, it can privately use that information to verify finality. So for example, let's suppose that 72% of Ethereum staking is done in Antarctica. And let's suppose Antarctica suddenly gets blown up by a nuclear war. Oh no, 72% offline. What am I gonna do? So in a traditional BFT context, right, you just don't finalize anything. You lose any notion of finality at all. But here, if I, as a validator, privately know that Antarctica has been blown up and 72% of the proof of stake validators are gone, then I can use that information and incorporate it into the fortress or into the finality gadget. So I can say, oh, I am going to reduce my threshold from 2/3 to 2/3 times 28%. And then to me privately, the chain is going to keep giving me guarantees of safety that are conditional on my own information. You could potentially do even more advanced things. So you could potentially have an opinion that some particular subset of validators is more trustworthy in some way. And so you could just privately assign them more weight. So there's this extremely large space of things that individual clients can just personally do. And the responsibility of figuring out what level of safety guarantees they have is sort of offloaded to the edges. Now, there are simple heuristics you can use, like for example, the 1/2 plus P 2-round Queeg oracle. But if you have more information, then you can use it. So you get, another benefit is that you get some amount of safety with just any amount online over 1/2, right? So if only half of Antarctica gets blown up, and 36% of validators go offline, in Casper FFG and in Tendermint and in these BFT algorithms, then basically they're either going to halt or they're going to stop finalizing, and you lose any guarantee. In Casper CBC, you still get potential, depending on what your oracles are, somewhere between 8 to 16% safety margins. So you still get kind of as much safety margin as you can get under more extreme circumstances. Another benefit is that this can be kind of bolted onto existing chain-based proof-of-stake blockchains very cleanly, right? So even just existing chains, if take NXT, Peercoin, like any of these, if they are willing to switch to LMD Ghost, then which actually is not that much of a switch, because under quote normal conditions, like LMD Ghost tends to just agree with whatever the fortress rule before was saying, then they could just have nodes privately run these safety oracles, give this extra safety guarantee, add these some slashing conditions, and you have a Casper CBC system. It's extremely flexible. There's lots of different ways to kind of implement it and bolt it on top of other things. So why upgrade to CBC? Why isn't Casper FFG good enough, right? So honestly, FFG is kind of ugly. And the reason why is because it kind of glues together the FFG fork choice rule, which basically says highest justified epoch wins, with some underlying fork choice rule. So in the original Casper FFG paper, it will be gluing together the FFG fork choice with proof of work. In the current Ethereum Beacon Chain implementation, it's gluing together FFG fork choice with LMD Ghost. And this kind of ugliness has practical consequences. There's kind of bounce back and forth attacks between two chains, and there are ways to fix these attacks, but they're definitely less clean than what you've just seen from a CBC Casper, right? So that's one of the kind of bigger reasons, just increasing kind of conceptual simplicity and just decreasing the conceptual attack surface of the design, but also all of these other benefits of CBC that I talked about. So why is the Ethereum 2.0 phase 0 not using CBC, right? Why is it still using FFG? So one of the big reasons why we were not able to do this earlier was efficiency. So basically, the problem with implementing CBC is that you have these two conditions that you need to enforce. One of them is this validity condition I mentioned, which is for a block to be valid under the Casper CBC rules, the block needs to be the building on top of what the chain itself kind of thinks is the head of the chain, like in some sense, right? So the block itself needs to contain evidence that shows that the person creating the block has the right to build that particular block at that time on top of that particular parent. And this requires like basically executing the LMD ghost fork choice rule in protocol as part of the validity condition of a block. So in English, this basically says in order for a block B to be valid, it must be the case that given all the evidence included in B or its predecessors, B is the correct block to build. Slashing condition. This is the only CBC slashing condition. We're down to one. If a validator creates two messages, M1 and M2, where M1 does not reference M2 and M2 does not reference M1, then the validator's deposit can be slashed. So every message that you make has to reference the previous message that you made, and the chain that you're building on has to like basically include a superset of all of that information. So everything you say must reference the previous thing you said, forming a single personal kind of message chain. So the implication is that if you make a block that took into account some piece of evidence, all future blocks must also take into account that evidence. The problem is, of course, we have a beacon chain. We have a huge number of validators that are making messages very quickly. We make this practical in a Casper FFG context with kind of separating out blocks and attestations. So we have one block every 6 seconds, potentially thousands of attestations every 6 seconds. And we use this cryptographic technique called BLS aggregation that allows us to combine together a huge amount of signatures into one signature that in terms of data complexity requires 1 bit per participant. And in terms of computational complexity requires 1 EC add, which is maybe 1 or a few microseconds per validator. The problem is that BLS aggregation requires many validators to be signing the same message, but CBC Casper kind of goes against that, right? So CBC Casper says every validator's message must reference that validator's previous message. And so it sounds like we're requiring validators to be each signing different things, which sounds like it might make BLS aggregation efficiently impossible. So here's a solution. Every block maintains a Merkle tree of every validator's most recent message. And so the way that you make sure that each validator builds on their previous message is that each validator builds on a Merkle root, which is the same Merkle root for everyone, containing everyone's previous messages. So a slashing condition basically says if a validator signs a message at slot C of a block where their most recent message was at some slot A before C, and they signed another message at slot B that's between A and C, then they get penalized. So challenges, right? Computing LMD Ghost takes a huge amount of time. There's this other version of Ghost called Bitwise LMD Ghost, where instead of going block by block, you kind of make it even more finer grains and you go bit by bit in block hashes. And it turns out that this has a relatively efficient algorithm where you can store information inside of the chain about whether or not, like basically the chain is valid. So for every validator, you can basically, there's this algorithm that you can use, and you can basically get verification of LMD Ghost in something close to kind of k times some logarithmic time if there are k validators that are being changed per slot. So this is actually not much more expensive than what's happening already, where you have that many changes already happening to a Merkle tree. So these things are definitely possible. Now, what does this mean, right? So first of all, Casper CBC can just be bolted onto existing systems, including any form of proof of stake. But also, this means that Casper CBC has this path toward kind of potential faster deployment in Ethereum in a way that actually changes surprisingly little of how Ethereum itself kind of fundamentally works today, right? So CBC is definitely not something that's happening in phase 0 or phase 1, but it's also, there's no need for CBC Casper to be kind of Ethereum 3.0 territory. It's something that we can start getting the benefits of more quickly. Thank you. Thank you.
Cool. Thanks, V. So next up, we have someone who over the past year has been super critical and super awesome in pushing the ETH2 space forward. So let's give a warm welcome to Danny Ryan.
Hello, I'm Danny Ryan. I work with the Ethereum Foundation. I spend almost all of my time on Ethereum 2.0 research, specifications, some client development, client coordination. I run some calls. I try to do everything to help just move this thing forward. Today I want to talk to you about the state of Ethereum 2.0. We have a number of awesome talks coming up in the next few days with some researchers, Vitalik started off, and clients. And so I want to just ground you in what the hell has been going on, a little bit about the architecture, and what we expect moving forward. So the past 12 months, quick recap. So 12 months ago, this project didn't exist. We had 2 major scaling and protocol upgrade efforts happening in parallel. It was the hybrid Casper proof of stake, proof of work embedded into a contract, and sharding via the sharding manager contract, in which the shard chains were kind of like bolted on to the existing system, managed in a contract. Both of these were system level contracts, meaning that they're recognized by the protocol as containing information relevant to the consensus. And both of them were happening really in most of the complexity was managed inside of these contracts in the EVM. So there were a lot of progress was made, and EIP was written on the Casper work, and a couple of clients were developing that. And there were some prototypes going on with the sharding SMC, but we were running into some issues, primarily issues by trying to bolt this onto an existing system and trying to doing complex things inside of the EVM. A lot of the issues were around trying to process a high number of signatures in the EVM, which was limiting the amount of validators that could participate in these games, and ultimately limiting the decentralization and scalability of the systems. So we deprecated both these work streams and unified them, Casper, Heart, Sharding, deprecated them into a new, much more radical design that's been deemed ETH 2.0 as the ultimate vision of Serenity. This radical new design has allowed us to make more bold decisions, re-architect from the ground up, and give us really a truly decentralized, scalable blockchain that we've all been looking for. So mid-2018, lots of research, lots of design. A lot of the components of the research were there, but it was really this effort of kind of figuring out how everything was going to fit together into a more concrete spec that people could begin working on. A lot of work in ETH research. We had a couple of Python proof of concepts, and this like HackMD proto spec. If you were a client implementer at the time, it was kind of a nightmare to follow the changes there. As we got towards DevCon, we moved everything into a specs repo where we had change logs, client implementing teams really were ramping up at the time, beginning to participate a lot more in the conversation and build out some proto clients. And we have these 2.0 calls. We had a workshop. This is a picture of a workshop in Prague. It was incredibly productive, getting us all in the same room, and super cold. We're all wearing like jackets in this warehouse. It was a good time. Prototypes beginning to happen, and the bones at this point, I'd say, of the spec were in place, but we were still in for some major revisions over the coming months. Come January 31st, we had an internal deadline of having a feature complete spec release. This is the first release, the January pre-release. of the phase 0 spec, and I'll go into a little bit what these phases are. And this, for me and for the clients, was really the mark of, okay, we're out of research, we're into a full-blown engineering effort. And really, although there was a ton of client work going on before then, most of the incredible progress has really happened since this time point. So through today, there are a number of, well, congratulations, there are a number of testnets, single client testnets out, and a number that are in the works. It's been super exciting for me personally, just to be working on this project for so long and to finally see and feel something tangible. Super pumped. This is just some dump of I think maybe it's Nimbus. Actually, I'm not sure. Of a testnet. The phase 1 specs are happening rapidly in parallel. Major simplifications have been happening on that front. And as I said, the initial client testnets. And we just had another workshop a few days ago. Super productive, getting everyone in the same room. Okay, so I want to take a break from timeline and things and talk a little bit about the client architecture. I know, especially when I talk to community members, they're very, they're like, okay, I understand proof of work. I understand the single chain paradigm, but I really, you know, I was the guy that could explain everything to everyone, but I'm really struggling to understand the complexity of this new design. And so, yes, when you take one chain and you make 1,000 of them, there's more complexity. And when you move from proof of work to proof of stake, there's also much more complexity because proof of work, although it has its problems, a lot of the complexity is handled extra protocol. And so we're bringing that complexity in with proof of stake. So it is a little bit more complicated, but I believe we can get an intuition for it. And so, as I said, there's a lot of talks about this. So hopefully I can get you grounded in it. So we have the proof of work chain. We have, this is the chain we know and love, stable, chugging along, has the community, has a lot of economic activity. This, in the new system, primarily serves as the economic seeds for Ethereum 2.0, initially just handling validator deposits. And so, moving beyond the proof of work chain, we have the beacon chain. The beacon chain is the core system level chain for the entirety of this new system. It's where the validators live. It's where finality occurs. So proof of stake finality, where we come to consensus on what is the head of the chain. There's an RNG in there, so random number generation via the participation and commitments of different validators. It's where the validator deposits live. So the rewards, the penalties, slashing, all of that occurs there. Rewards being, if you do your job well, you get rewarded. If you do your job poorly, you get penalized. There's also a group component to that. So if we all do our jobs well together, we all make a little bit more money. Whereas if we're all doing a crappy job, we might lose more money. And this notion of this thing we call the shuffling. Validators have a number of duties at any given time, and the combination of the current validator set with the output of the RNG dictates what validators need to be doing. So this beacon chain, it's a system level chain. It's no user activity happens here. It's just the core consensus of the system. It also serves as the backbone, or maybe the spine of the chain, where the shard chains are connected to. Shard chains are much more what we think of as a blockchain, at least from a user level perspective. The shard chains, each of these you can think of as like similar to the Ethereum 1.0 chain, where it has accounts and transactions and user level activity. These shard chains are, I think I have a, oh cool. These shard chains are connected back to the beacon chain via, we'll call these things crosslinks. And so one of the main jobs as a validator is you're assigned to a shard chain where you sync to the shard chain, attest to the availability of the data, and you sign a commitment attempting to make a crosslink back in. And so we take these recent references of shard chains and put them into the beacon chain. Now this reference does a number of things. One, the primary thing it does is that it routes the shard chain back into the beacon chain. And by doing this, to find the head of a shard chain, I find the head of the beacon chain, I find the crosslink, the latest crosslink for the associated shard, I go to that block, I'm now at the shard chain and I find the head from there. And so it unifies the consensus of the shard chain back into the beacon chain. The other primary thing that these crosslinks do is they serve for the basis of asynchronous communication between shards. So if I have a user level transaction right here on shard 1 that wants to communicate to shard 1024, a crosslink is made. And then a crosslink, once the crosslink is made, a receipt that was emitted over here, because the shard chain over here knows about the root of the beacon chain, a claim can be made about this crosslink, about this receipt. The receipt is consumed and enacts essentially a transaction on the other. So these crosslinks really unify and bring the shard chains back into the beacon chain. And so, right, so we have beacon chain, we have shard chains. And so as a validator, what I do, I have two main roles. One is to create these crosslinks, and the other is to serve a little bit on a longer term role on the shard chain. So maybe every week or two, I get rotated from one shard to another, building the shard and creating the user level blockchains. Beyond that, we have state execution. So we have the data here, and then we have a layer 1 interpretation of that data, a VM, almost certainly WASM, still some stuff to work through there. Okay, so general architecture is generally what's going on. People are going to be going into a lot more detail on how that manifests in clients and some of the research around the different components throughout the next few days. Outside the core architecture, we have serialization algorithms, tree hashing, which is kind of a fun little way to take any object and hash it into a Merkle tree to make proofs about them. BLS 12381 and BLS aggregation, networking and discovery, libp2p, which is a modular P2P networking stack, Merkle proof formats, light client protocols, test formats. There's all sorts of stuff that sits right outside of this core architecture that really kind of puts the clients really together. Cool. Phases of development. So the development of ETH 2.0 is divided broadly into 3 phases right now. This is to help manage the complexity. Phase 0 is the beacon chain. It's the core system level chain, simply just a validator-based proof of stake chain. This is what has been primarily worked on with respect to the client development so far. And we do expect to launch simply this core chain without any user level activity. This is for a conservative approach, although it would be mainnet with real ETH and real rewards and penalties. It does give us some, allows us to coordinate in the case of some instabilities or any issues that arise without having to deal with user level activity. Phase 1 brings in the shard chains, but just shard chains as data. So just coming to consensus on this data, being able to build these chains, link them back into the beacon chain. It does not have user level activity still. It doesn't have a VM, an enshrined VM, transactions, accounts, the things that you're used to. And this is, again, to grow from the center out, adding complexity. This is largely a networking problem, and something that I expect to launch not too far after this phase 0. Phase 2 is to add a enshrined layer 1 interpretation of the data. So adding accounts, contracts, the VM, transactions, state executions, and the cross-shard transactions, cross-shard communications. This, I say a layer 1 interpretation because although prior to phase 1, we can still use this data layer for interesting things. Anytime we come to consensus on data, anyone layer 2 can choose to interpret that data however they want. There's lots of cool scaling solutions you can do just with the data. So those are the primary phases of this core architecture. There's some stuff we've been talking about that we want to do in parallel. This is not 1x. These are potential things that we want to do to improve 1.0 utilizing 2.0 while 2.0 is being developed. One thing that we wanted to do is utilize the 2.0 beacon chain to finalize the 1.0 chain. This is very similar to the Casper, the hybrid proof of work, proof of stake, where we're using a contract to finalize the proof of work chain. We can use the beacon chain in the same way. Seems like a lot of the community members are pretty into this idea of leveraging the security of the proof of work chain with the validators and potentially reducing rewards. After that, we can expose the 2.0 state roots. So the beacon chain state root, you can make proofs via the beacon chain state root about the data and state of any of the shards. So by exposing the 2.0 state root in 1.0, we can then leverage the shard chain data layer for tons of interesting scalable things. Like the one thing that's really been talked about is using it as a data availability layer for ZK rollup. Phase. And these are not canonical letters. I just threw them out there, and they're a little bit in flux. But phase C, with at least through phase 0 and 1, there's no fungibility between these two systems, between the ether on these two systems, and it's definitely something that the community is interested in. So as we move along this, if we have finalized and we are exposing the state roots, there are some options on doing fungibility. So if the community is really interested in it and it's technically feasible, it might go down that path. And then phase D is really just, what do we do with the 1.0 chain? There's a number of options. One might be to roll, and I won't go into detail right now, don't have too much time, but roll the 1.0 chain into 2.0, probably via a stateless contract, or keeping it living as this like external appendage of the system that highly uses the security of the 2.0 chain and just kind of lives in perpetuity. There's some trade-offs here, some different technical challenges, and really it boils down to what the community really wants to see. Progress is being made on all of these. A lot of this depends on light clients, 2.0 light clients. But again, progress is made, highly in flux still. The path from here, much work, many hands. That's not a minus sign, that's a tilde. Somebody pointed out it looks like a minus. There's approximately 100 people working on this, which is wild. There are 10 clients, roughly, of various commitment, size, stability, etc. I wasn't going to name them all, but I think I'm going to try to name them all. Okay. Trinity, Nimbus, Lodestar, Lighthouse, Prism, Yeath, Parody, Geth has some stuff working. Oh man. Harmony. Somebody help me, I'm sorry. Artemis, yes. And then there's an executable PySpec and an executable GhostTech. So there's a lot of people touching this thing. And beyond that, they have, we have libp2p, the protocol labs guys are working. We have Whitebox working on this. Pegasus has a research team outside of the EF. Like there are, I'm sorry, I shouldn't have named anybody because I'm not going to name everybody, but there's tons of people working on this. It's super exciting. Okay, what to expect? Those emojis are broken. Sorry about that. Q2, we're going to freeze the phase 0 spec. Clients are going to be stabilizing and optimizing. We're going to see more single client and multi-client, probably short-lived testnets, and continue this phase 0 spec development. Upcoming client challenges in this quarter and the next. Really, clients are the unsung heroes of this. They're taking these like crazy ideas and making them a reality, and to take that and like make it a production client and like a production piece of software is like a huge undertaking. So they're going to be passing consensus tests, they're going to be optimizations up to 4 million validators, efficient aggregation strategies both in terms of computation and bandwidth. They're going to be seeking stable networks, they're going to be doing state sync strategies, working on validator UI UX, security reviews, visualization tools. The list goes on. There's a lot of work to do. They're doing the hard work. If you please thank your client developers and honestly fund your client developers. Q3, audits and formal verification, cross-client CI and fuzzing as we also increase just the test vectors. We'll be doing some network stress tests, start to see long-standing multi-client test nets, and phase 1 and phase 2 spec development. Somewhere, I'm not going to claim when we're going to freeze phase 1 spec development, but it's going to be getting pretty stable, and at that point, might have a couple of clients do some prototyping. Q4, towards phase 0 launch. Somewhere, definitely around this time, we will be coming up with a launch plan and enacting it. There's some unknowns between here and there and stability of networks, but we're going to be getting close to this point. Phase 1, I expect to be stable and in development, and phase 2, the spec will be maturing. TLDR, it's happening. It's super exciting. If you want to get involved, talk to me, talk to the clients. There's a ton to do. And thank you.
Thanks, Danny. I feel much more knowledgeable about the wonderful, crazy world of ETH2. So next up, we have yet another researcher, Ethereum Foundation rockstar, who's going to be telling us about a life in the day of a beacon chain validator. So let's give a round of applause for Hsiao-Wei Wang.
Hello everyone. So today we already have the two wonderful talks talk about the Ethereum 2.0 architecture and roadmap. And my talk is about, I'm Hsiao-Wei Wang from Ethereum Foundation Research. Thanks, Ben, for the introduction. And my talk is about the life of an Ethereum Beacon Chain Validators. So it's about the life cycle and what's the responsibility of the Beacon Chain Validator. Okay. So a quick recap of where we are. We already seen that diagram before, and my talk will focus on the beacon chain part. So the beacon chain is a whole new chain here. It has to be joining from the ETH1 chain contract, and it has its own genesis from in the beacon chain. And that's the roadmap. I will focus on the beacon chain phase 0 and see that what we already have and what we will do. So first question is that why would people want to join the beacon chain and become a validator? The answer is simple, because there are incentives of the rewards for the validators to get. So the reward includes that. So first, it's similar to ETH1 miners. To be a validator, you can include as many transactions as you can. So there are two. Currently, we have two types of we call that operations can make can get the fee from them. One is the transfer, and another one is we call that the attestations. So attestation is you can see that as just votes. You can vote for which block you think that's the valid block. And in this attestations, it includes the aggregated signatures. So, but for the individual validators, they have to sign for some specific attestations. So once you actually sign for that message, you have to be responsible of that. If you sign something that is actually incorrect, you will be punished later. Okay, so that's the attestations. So the validators they can get rewards from include as many attestations as they can. The second rewards from for the proposers is that they can become the whistleblower. So whistleblower is that So as I said that some validators, some dishonest validators, they may sign something invalid. So if you are honest validators, you can to report to the other validators that, hey, this guy, he did something very bad and please let's stash it. So once this stashing message be broadcast into the network and then it be included into the block, then the money, the ether from the stash validator will go to the whistleblower. So that's a mechanism to prevent that people to do the bad thing and to incentive that people to be justice and to make the chain safe. Sorry. And the second kind of rewards is the FFG rewards. So it's about that you are really vote for the correct valid chain of the beacon chain. And there are third type of the reward is we call that the cross-link rewards. Cross-link is the link between the shard chain and the beacon chain. So when the attestation, the validators, they make attestation. At the same time, they also make cross-link. So this cross-link will link to the shard chains and to attest that which shard chain you are validate and is that which the block of the shard block is valid in your view. So those are the three types of the rewards in our current spec that can make a validator to get reward. And now you know that why we want to become a validator. And second question here is that how to become a validator. So how to join the staking? So there will be a special contract on the ETH1 chain. We call that the deposit contract. So every user, they can make a deposit of 30. Right now it's the 32 Ether to this special contract. And after they make deposit, the validators can watch the logs, the event logs from the ETH1 deposit contract, and once the deposit already be mapped into the contract, it will emit a special logs. So once the validator, they can be a light client of the ETH1 chain and then listen and watch these logs to see if my deposit is already being accepted in the ETH1 chain, and also if other validators are joining the new chain. Okay, so if there's a lifecycle graph that we assume that the validator already be a deposit from in the ETH1 chain. And also we have to make sure that it did deposit enough balance and it's ready to be active. Well, note that not the validator doesn't be active immediately once they deposit. They need to wait for like right now it's the 25 minutes, at least 4 epochs time to be activated. Then the third part is that once the validators are activated, they become, we call that they are the active validators. And the active validators will be added into a long validator registry list. Please know that it has to be one single huge list because we are going to make the pseudo sampling from the one single validator pool. That's as we talked about that previously, there's very important in the beacon chain component is the randomness. The randomness provide to us have the ability to make pseudo randomly sample of by the shuffling function. And the third part is that what should the validator do in this context? So right now I'm only talk about is the responsibilities in phase 0. They have two main jobs to do. The number one is they have to propose a valid beacon block. And second thing is that it has to create the attestations. So this is the current architecture, current data structure of the beacon block we have. There are two notable things in the block body. One is the random review. In ETH2, we now use the random to provide the randomness in the system. And every proposer, when they propose their block, they have to provide their own random review, and that will be the part of the entropy to create the randomness seed. That's how the randomness goes. And the second part is that they have to choose the best vote of the ETH1 chain reference. That's the link between the ETH2 chain into the ETH1 chain here. So the as I said, that the validators of the beacon chain validators, they have to be kind of the like-kind of the ETH1 chain. That's the link between them. And also they have to include the beacon operations in the beacon block bodies here. Now we have different types of the operations. There are the list is like proposer, stashings, the stashing messages, and attestations. Also, the deposit message has to be included here, and then we have the how to validity exit. It will be messaged in here. Okay. And the second important thing is to create attestations. The attestations message has 3 parts. Thanks for the refactoring by Danny. It's much more better now if you are client devs. And they have 3 parts. That one is the they will have to vote for 3 things. One is they have to vote for the ETH1 chain block, and second one is that they have to vote for the beacon block, and third one is the shard chain block. We also call that the cross link. So yeah, so you can see that because the beacon chain validators, they are in the core layer between the main chain, the ETH1 main chain, and the shard chains. So they have to be the bridge between them. Okay. And the incentive is not only the rewards. There are also the stash to the dishonest validators to improve them from being malicious. There are different types of the penalties. One is the FFG penalties. So if the validators they contribute to the FFG finalizations penalty, they will get rewards. But if they didn't, they will get punished. Then there's also the inactivity leak stashes penalties. That's for that if the chain doesn't being finalized normally, that's because like maybe we didn't get the threshold like 2/3. So that time we will punish the validators that they didn't do their job well. Third part is the cross-link penalties. It's similar to the above, but it's focused on the shard chain votes. And there are also the 2 types of the slashings. One is for the proposer, and another is for the tester. So, yeah. and also the proof of custody gain penalties. So after me, Justin will talk about that deeper. Okay, then let's see the validator trump. And it's driven by the total balance here. We have some calculations functions that to calculate what's the max balance trump we have right now. So right now in the version 0.51 spec, there are two queues in the last spec. One is the activation waiting queue, and another is the withdrawal queue. But there are work in progress PR here by Vitalik. His suggestion we can use the exit queue instead of the withdrawal queue here. Okay. And then once the validators are being active, doing their job, but what about one day they just don't want to do it anymore? They want to exit. What can they do that? Yes, good news is that we have the voluntary exit message here. So the validator, they can send the voluntary exit operation to the network, and if it's it will be a message that be included by the block proposer. And about the withdrawal that most people care about, unfortunately, in phase 0, we only can make them into a withdrawable state because for now there's no state machine in the beacon chain. But good news is that in phase 2, we will make them withdrawable from withdrawable state to withdrawn. And the validator index will be recyclable here. Okay, so let's see the diagram again. So now the validators are already being activated. And there are three types of the phase that three types of the routes they might do. One is that they might get slashed. And if they get slashed, they will be exit too. So you can notice that to stable the validator, to stabilize the active validators, the size of the active validators should be kind of stable. It can be updated too frequently for the network security. And then so that's why the validators don't trump immediately. They have to wait for a while time, and then they got slash and exit state. And then after like 36 days, they got withdrawable state. And the second type is that they may got ejected because they don't have sufficient balance in their account. So that's a similar case that they will wait for 4 epochs, 25 minutes, and they got unslashed, but they exit. And then wait for a while to be in the withdrawable queue, and then they can get withdrawable state. The third part is the voluntary exit case. But please note that the diagram might be updated later after the work in progress PR be merged. So that's what the current validator status would be transition. Oh, and also the unslashed and exited state might be go up to another path because of while they are waiting for being exit, something might change between when they are waiting for that. Okay, and I want to talk about that some computation and network requirements in our current system here. So as Vitalik already mentioned that the worst case is that we have like 4 million validators in the beacon state. So imagine that 4 million validators in a single array, and we want to make the community shuffling of this 4 million array. So it takes time, and also we have to improve the beacon state cache management, of course, because to update the state of the validators would be hard than in the huge case. Another issues here is the networking propagation. So we have different types of the messages, like the beacon block, the attestations, and other transactions. So some of this message needs to be broadcast to the whole beacon chain universe. But maybe some messages like the attestations, it only needs to be applied to be broadcasted to the shard network, we call. So imagine that we have like 1,024 shard chains. Each shard chain has their local messages for the shard blocks, and attestations has to be aggregate in the shard block network, because if we broadcast all the message to the whole network, it will be too noise in the network. And also, as we said that we want to stable the shard chain validator shuffling, but for the security, the validators has to be assigned to different shard committee after a while. So, but although it doesn't happen frequently, it still needs time to, like I have a validator in the shard 1, I want to switch to shard 2. But when I want to do the switch between the networks, I have to sync from the shard chain 1 to shard chain 2. So how to do the fast sync immediately? That's a question we are going to think about deeper. And the third part is the BOS signature aggregations. So right now we expect that it will be like 128 validators in each committee. But if we think about the worst case, there'll be 4 million validators. So do the basic calculations. In the worst case, that there will be like 65,000 of the individual signatures per second. So of course, now we need to aggregate the signatures. So that's another hard question in engineering that we want to solve. And if you are interested in the BOS, there are the working progress spec, but we are going to but it's another version, and we want to standardize this in the few months. And speaking of the stabilizing the specs, we have there are 3 different main kinds of the specs. One is the phase 0 specs, including the core, the serialization, the SSZ, and BOS signatures. There are also 2 other work in progress things in our mind, but there is the networking specs. Thanks from the Matt from Qualcomm, they are very helpful for us. And also the validator interface spec that we are thinking about it. So yeah, that's what we are working right now. So if you are interested in contributing, I'm happy to chat with you on the Gitter. And also I'm working on the Trinity, the Python client implementation here. Thank you.
Thank you, Hsiao-Wei. That was great. I think I've got to start saving up so I can have 32 ETH and become a validator. So last but not least, in our trifecta of awesome Ethereum 2.0 researchers, I'd like to welcome to the stage to talk about the ETH2 custody game, Justin Drake. Woo!
Okay, thank you. Let's go back. Okay, so I'm going to talk about phase 1 of Ethereum 2.0, which is the data layer. And specifically, I'm going to talk about the data availability problem, which comes with having lots of data. And even more specifically, I'm going to talk about the custody game, which is one of the solutions to data availability. So 3 parts in the talk. What is the data availability problem? What are some of the solutions that we intend to deploy in phase 1 and in the future? And then a deep dive into the custody bit game, which was recently simplified. Okay, so what is the data availability problem? So basically, you have data, and you can reference that data with some sort of identifier, which is succinct, like a 32-bit byte hash. And the question is, if you're only given the hash and you don't have the data, is the data available to you? Can you actually go ahead and download it? And one very simple approach, which is kind of the naive brute force approach, is that you just go ahead and try to download the data, and then you will know whether or not you can download the data. And that's perfectly fine for Ethereum 1.0 and for the Beacon chain, because these are very small chains, and every validator, which we assume to be a laptop on a home connection, can download without any problems. But this is unscalable, this kind of naive approach, especially in the context of sharding. So even though one single shard has totally reasonable bandwidth, let's say on the order of 1 megabyte per minute, once you have 1,000 shards, then it becomes a lot more data on the order of 1 gigabyte per minute. And so, how do we deal with all this data? And the scalability solution of Ethereum 2.0 is that everyone doesn't download all the data, and there's just too much data for the validators to download. So what we do is that we take the shards and we kind of segment them into epochs, and then for each epoch we have so-called cross-link data, which is going to be the data in the shards plus the data in the headers. And this cross-link data, let's say, is 16 megabits, which is 2 megabytes. And the reason I'm talking in bits will be relevant later. And what we have is that we have these references from the beacon chain to the shard data. So we have these so-called crosslinks, which are the yellow stars, and the hashes, which are the purple rectangles, and they're pointing to data. And so as a validator of the beacon chain, you only see these very succinct crosslinks, and you want to have high guarantees that the data that these crosslinks are pointing to are indeed available. Okay, so let's not look too much as to what's in the data. We can forget its blocks and headers. Let's just assume it's a blob of data. And what are the steps to kind of creating a crosslink in Ethereum 2.0. So the first step is to Merkleize. So we have this hash tree root. So instead of taking a simple hash, we Merkleize. So that, just a detail. We have this identifier, which is a data root. And then the attesters, which are basically validators in a committee assigned to this very specific crosslink data, are meant to download the data and sign it if they are able to sign it. So they're kind of vouching that the data is available, is downloadable. And then the various attestations are aggregated across the committee using BLS aggregation. And then once you reach a certain threshold, which is enshrined in the protocol, then you get the yellow star and you are a crosslink. And these crosslinks go in the beacon chain. And so, to rephrase the data availability problem, how do we know that from the crosslink, you can recover the data if you're not a validator that, was assigned to this specific crosslink. And the reason that you really want to know that the data is available is that if, for some reason or another, this data is not available, then that means that you can't download it. The network in general can't download it. Then you have a so-called unavailable crosslink. And this is like super toxic waste that will pollute the beacon chain extremely fast. And so if this happens, then emergency mechanisms need to come in place. We need to do manual rollback all the way back to when there wasn't this unavailable crosslink. So this is one of the main problems of phase one, and we're going to see how we can solve this problem. So in phase one, we're going to have three solutions to the data availability problem. So one is going to involve cross-linking, which is a process that just walks through, but I will give more details as to why it works. And then we're going to go through custody proofs, which is like the main content of this talk. And then there's also a mechanism, which is the chunk challenges. And you can kind of think of them as kind of on a time axis, where the custody proofs are proofs that you have the data, and you can only build them when you have the data. So they're kind of before even committing to having the data. So they're kind of in the past relative to the crosslink. Crosslink is like a real-time thing. You're committing to having seen the data in real time. And then the chunk challenges is basically a thing that happens post facto, which is, oh, you committed to this data. Please give me this random chunk of the data that happens post facto. And then in phase 3, plus, or maybe in Ethereum 3.0, we don't really know, or maybe even in phase 2, if we're very aggressive, we have something more fancy, which we call availability proofs, and these use kind of fancy math and tricks like erasure codes and Starks. And I won't go into details. That's, I guess, for another talk. Okay, so let's see why crosslinks work. So the reason crosslinks works under a certain security model that we have in Ethereum 2.0, namely that an honest majority assumption, is because we have this pool, a very large pool, let's say 1 million validators, and we're assuming that 2/3 are honest. So they will follow the protocol rules, which include downloading the data. So 2/3 are honest, 2/3 are angels, and then 1/3 are demons. And when you have a pretty good random number generator, such as Randall, then and you have a crosslink committee, which is around 1,000 validators, then with extremely high probability, at least 1/2 of the validator is honest. So you lose a little bit of honesty going from the pool to the committee, but it's not too bad. And then, because you have this threshold in the crosslink, you can make the threshold large enough, and so in this case, you make it greater than 1/2, and then you have a guarantee with a very high probability that at least one, if you do reach the threshold, at least one of the voters will be honest. And so being honest means that you've actually have downloaded the data, it's on your computer, and if someone requests it from you, you'll share it with them. So the data is available to the whole network. Okay, but there is one problem with crosslinks, and it's due to this kind of misalignment of incentives. So there's two ways to go about crosslinks. So the honest way is basically you have this chunk of data, which is quite large, and you need to go ahead and download it. And only after downloading it, you sign your attestation, and then because you did all this work, we will reward you in the protocol. And this is kind of the approach where you need to do all this work, and you have this man that's sweating. But then there's the other approach, which is kind of cheating, which is you have other people that are making votes. these attestations, and you just kind of look at what other people are doing, and you kind of copy what you're doing. So it's kind of a copycat strategy. And seeing what other people are voting on is very cheap because these votes are very succinct. And so you can just follow the crowd and still get the rewards. And this is basically the light node approach, which is the lazy approach. And it's kind of like SPV mining in Bitcoin. And it's kind of bad because if you have an attacker, which is not necessarily that's huge, but like significant, they can vote for an unavailable crosslink, and then all the lazy people will pile on, and then you'll reach the threshold, and then you have an unavailable crosslink. So that's kind of bad. So one of the key idea is that in addition to signing the data, you're going to tag on this proof of custody, which is this kind of really cool construction, which is just you're going to tag on just one single bit, either 0 or 1, in your attestation, and that is going to prevent or disincentivize people to be lazy. Because if people are lazy and they don't download the data, then with probability 1/2, they're going to mess up the proof of custody, and so they're going to get slashed. So as a now as a validator, if you want to be lazy, what are you gaining? You're just gaining a little bit of bandwidth. It's a very minimal gain, but what do you stand to lose? You stand to lose your deposit with high probability. And what we've done basically here is that we've upgraded the security assumption of crosslinks, which was honest majority, to something closer to rational majority. So there's kind of there's the honest people, and then there's the rational, are the kind of two extremes. And there's all sorts of things that go in between honesty and rationality. So one of the things in the gap is going to be laziness, and that's specifically what we're targeting. I mean, there's other things that can happen like collusion and bribing, which we're not addressing here, but laziness is what we are addressing. Okay, and same thing here. With extremely high probability, you're going to have at least one honest but lazy a validator, and they're going to actually do the work because of the proof of custody. Okay, chunk challenges. These are very easy. So let's assume that you've signed an attestation, so you've committed to the fact that you've downloaded some data, and the data. Someone might want to make a query about the data, and they say, just give me this chunk at random. And the response needs to be fed on the beacon chain, so everyone is aware of the beacon chain, and the beacon chain itself is available through this brute force approach of everyone just downloading it. And the reason why we have a small chunk as opposed to the whole data is because the beacon chain has very limited bandwidth, and so we can only afford to put these small chunks. And then in addition to the small chunk, you also have a Merkle proof that the chunk does indeed match the crosslink and the index, basically the location in the data that was in the challenge. Okay, so now to the most interesting bit, which is the custody bit game. So how do we basically enhance these attestations by adding one single bit in such a way that if you don't download the data, you will be caught half of the time. So just to reframe the problem again, slightly more abstractly. So you have the data, you have the data root, the signature, both form an attestation, and you want to basically have a so-called custody bit, which is basically a cryptoeconomic construction. So it's not a cryptographic thing. It's not like cryptographically with very high probability that that person has downloaded the data. You basically weaken that a little bit and say that with probability 1/2, if they got it wrong, with probability 1/2, they will only get it right. They will only get the custody bit right with probability 1/2, and they'll get it wrong with probability 1/2. And we will know about this at some point in the future, in the near future. Okay, so just a quick note about why one single bit is kind of a very nice property to have. And the reason is related to aggregation. So BLS aggregation is a signature aggregation technique which works extremely well when you're aggregating the same message. So the verification cost technically is like going to be like one pairing per message. It doesn't matter how many people are signing it, you still have this basic cost. But as soon as you have multiple messages being signed, you need to pay these multiple pairings. And when you only have two types of messages, attestation plus the bit 1, attestation plus the bit 2, then you can just aggregate them separately, and your verification cost only doubled, and it's still marginal. So basically, in the optimistic case, where people get the proof of the custody bit correct, then there's very little overhead to the beacon chain. And if people are doing very stupid things, like not downloading the data but still participating in the attestations, then they'll get caught, and there will be a challenge game to basically slash them. Okay, so what is kind of one of the key ideas in the construction? So you have the data, and you want to come up with a construction which kind of proves that you and only you have, you definitely have the data. So one of the ideas is that you introduce the notion of a key which is unique to you as a validator. So even though the data is generic to everyone, you have a key that is unique to you. And we're going to temporarily attach value to this key. So if you give the key to someone else, to some sort of outsourcing service, then that outsourcing service can use the key and take your money. So if you don't trust the outsourcing service, you really don't want to give them your key. Okay, so we have the data, we have this private key, and what we do is that we mix the data and the key really, really thoroughly, so that they kind of maximally combined. And then once we have this mix, which for example could be the XOR, so if you have the very long piece of data and a short key, you just XOR every single chunk in the data. That's one way of mixing. And then once you have this mix, you're going to extract one single random bit. So that's going to be using a so-called pseudo-random function, the PRF. And one way, for example, to extract a random bit is to take the hash of the mix and take the first bit of the hash. Okay, that's going to be random. And the whole point of this construction is that the only way to compute this custody bit is to have both the data and the key, and in particular, to have the data. So you have downloaded the data. And just to rephrase this non-outsourceability visually, you have the validator, they have the key, but they kind of want to be lazy. They want to outsource the downloading of the data to someone else. So someone else has the data. And unfortunately, in order to compute the custody bit, you need to combine the key and the data. So there's kind of two ways to combine from this setup. Way number one is to take the data and bring it to the left side. Well, that's kind of defeats the purpose, because now the validator actually has to download the data. So they've gained nothing from the outsourcing service. And the other option is to send the key to the right side, but that's not going to work for the validator, because then the outsourcing service has the key, and so they can steal the money from the validator. Okay, so let's go through like the whole dance in the scheme, in the protocol. So we have three phases: commit, reveal, and then challenge. So commit, you commit to having the data, then you're going to reveal your key, and then if the custody bit is wrong, you're going to be slashed. So off-chain, in the commit phase, you will generate your key, which is going to be unique and deterministic. You download the data, you compute the bit, and then you commit. Boom, that goes on-chain. Sometime later, you will reveal your key, and then once you reveal the key, basically your custody bit becomes publicly verifiable. Anyone, anywhere in the world who has the data now also has the key, and so they can verify off-chain. Does the mix, does the combination of the key and the data, match the custody bit that was in the initial commitment in the attestation. And if for some reason it does not match, then you challenge. You go on chain with the data and you say, hey, Beacon Chain, please compute this custody bit. It's wrong, and please slash the validator. And in addition to this slashing condition, we have another slashing condition, which I kind of been talking about explicitly, which is that if for some reason the key has been given to someone else, then you want to have this the slashing condition for leaking the key early before the reveal phase. Okay. Now there is one problem with this scheme here, and is that in the worst case, if validators have a bad custody bit, then in the challenge, the data is going to be like the whole crosslink data. It's going to be all 16 megabits. So that's too much data for the beacon chain. The beacon chain can only handle things like on the order of so-called chunks, which are about 4 kilobits, 4,000 bits. So how do we go from this very large piece of data, 16 megabits, to just 4 kilobits? And the trick is to basically take the data and cut it into 4,000 chunks, each chunk of size 4,000 bits. And then for each chunk, you compute a separate custody bit. And then you kind of combine these bits, the so-called chunk bits, you have 4,000 of those, into a final custody bit. So if you just ignore the middle bit, you still have a custodial PRF. So you still have a scheme which takes the data and produces 1 bit and guarantees that you have the data. But there's this kind of intermediate thing in the middle. And this intermediate thing allows you to challenge very efficiently. So if for some reason you disagree on the custody bit, then you will publish on-chain your version as a challenger of the intermediate bits, and then the original validator, it's their duty to either to point out where the challenger is wrong, so that they can come to agreement as to who is wrong. And if for some reason the challenger is not wrong, then it will be impossible for the original validator to point out an error in the challenger. And one kind of important detail here is basically the numbers that we've chosen. So notice that 4,000 is the square root of 16 million. And so it turns out that taking the square root is most efficient because you're going to have the number of chunks times the size of the chunk is going to be the size of the original file, and the challenge is going to be the sum of these two things, and so taking the square root is optimal. Anyway, that's a detail. But yeah, just to rephrase visually how the challenge game works, the only difference is now in the final step in the challenge, you provide these intermediate chunk bits, and then the validator, the original validator, has to point out where the challenger is wrong, if it is wrong. And the way they do that is that they provide the data to the beacon chain with the data and the key. The beacon chain can compute this intermediate bit. And of course, the data is authenticated against the crosslink. Okay, so this is one of my last slides. So this whole scheme is like pretty amazing. It's very cool that it exists. But one of the design considerations for Ethereum 2.0 is to be so-called MPC friendly, or friendly to staking pools and things like that. So we want to be able to take the notion of a validator, which is kind of logically a single entity, and behind the scenes, kind of off-chain, we want to allow users to take this validator and split it up into shares and have some, M of n logic. So there's two use cases for that. One is staking pools. So if you don't have the minimum amount of Ether required. For example, 32 ETH or 64 ETH. We don't know yet for sure. You can pool your funds with other people, and you each have kind of voting power in proportion to your stake. And then you can set a reasonable threshold within your staking pool, and basically have one single validator with multiple users behind it. The other use case for being MPC friendly is the idea of distributed staking. So you are a single validator, you have the 32 ETH, but you don't want to put all your eggs in a single machine. So what if this machine gets hacked? Or what if this machine goes offline? So what you can do is you can, for example, have 3 different machines, and you can set up 2 out of 3 validations, so that if you have 2 of the machines that are online, then the system keeps on running. And if you have only at most one machine that gets hacked, then your hotkey, which is going to be your hot validation key, can't get hacked. Okay, and in order to kind of be MPC friendly, we need every single part of all of Ethereum 2.0 to be MPC friendly. And there's going to be 3 different things that are specific to the to the custody bit scheme, which makes it tricky. But turns out there's these really nice constructions that involve, on the one hand, BLS signatures. So it's BLS is very good for these threshold signatures, and you can use threshold signatures as your key scheme, your secret. And we do the same thing for RANDAO. So RANDAO is a commit reveal scheme where you commit to something and then you reveal your entropy. One way to phrase this, one way to implement it, is you commit with your BLS pub key, and then the way you reveal is by signing a message. And because BLS signatures are unique and deterministic, you have a well-defined reveal. Anyway, and the other cool construction is for the PRF. So it turns out that this wonderful mathematical construction called the Legendre symbol, and it seems to fit exactly our needs. So it can take a chunk of bits, and it will generate a unique random bit out of it. And the whole thing is very MPC friendly. I think it's maybe 2 or 3 rounds of communication, which is great. Anyway, thank you. This was the whole scheme. If you want to read the specs, I encourage you. There's a draft right now, but it's pretty good. And yeah, also want to thank people who've been working on the spec. And that's it. Thank you.
Awesome, Justin. Thanks so much. All right, guys. So we're almost off to lunch. Before that, I have 3 quick announcements that we're going to make. So one of them is that, this is very cool. I've never been to a conference that does this before. But if you guys run into awesome people at this conference, or you are very excited because you're, get to share a room with people you don't always do that with, and you're hoping to have a place to hang out, it turns out that after the conference sort of official event ends, the rooms are still available for you to use. So if you go to the registration desk and talk to them about that, you can, I think, sort of reserve rooms to hang out after. So that's pretty cool. Second thing, speaking of workshops, at 1:30 p.m. today, Kyber and Sealand are doing a workshop in the sub-conference room. That may be 2 workshops, actually, I'm not positive. So feel free to go check that out. Those will be super exciting. And lastly, a very small thing, the organizers have noticed a lot of luggage floating through. Another cool thing that this venue turns out to offer is luggage checking. So if you go downstairs, there is complimentary bag checking, so you can have your bags in a safe place and don't have to clutter the halls or worry about them getting stolen. And with that, let's eat some food. So we'll bake for lunch.